Vikash, 11th F. Please mute. Ma, 11th E, Navya stay. Mute put ma. Please stay on the line.
Dear students, good morning to everyone.
Good morning, sir.
Can you hear my voice?
Good morning.
Yes, sir.
Good morning to everyone.
Good morning.
Good morning, sir.
Good morning,
Okay,
sir.
sir.
Good morning, sir.
Okay, students, today we start new structure for exception of octet rule. Can you hear my voice?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Rajkumar Raj,
Yes, sir.
can you hear my voice?
Yes, sir.
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
Dear students, can you hear my voice or not?
Yes, sir.
Anyone respond first?
Sir, yes, sir.
Hello?
Hello. Sir, yes, sir.
Yes,
Can you
sir.
hear my voice or not?
Yes, sir.
Please respond.
Yes, sir.
Yes, sir. We can hear, sir.
We can hear. It is audible.
Hello?
Yes, sir.
Please.
Yes, sir.
You can hear, sir.
Today, we are taking the Lewis structure for exception to octet rule. Exception to octet rule. What is an octet rule? Any electronic configuration is most stable. Any electronic configuration for an atom is most stable. To attain the octet structure, each element is reacted with another. An element is reacted with another to attain the stable noble gas electronic configuration, that is NS2 NP6 in the octet. Then it is known as octet. So, any electronic configuration around the atom is stable, so that here we are ready. Not only the 8 electronic configurations are stable, and so that there is an exception to octet rule to writing the Lewis structure. Okay, the first one we are taking, and here the octet rule is useful to writing. So listen, we are taking the octet rule. The octet rule is useful. Octet rule is useful for writing Lewis structure. Lewis structure. So, the octet rule is useful for writing Lewis structure for the molecule with the second period of an element. For the molecule, with second period. It is important. It is second period of element. Second period of a element as a central act. As central act. So it is perfectly suitable for second period of an element in the periodic table. What is the second period of an element in the periodic table? Here it is lithium, beryllium, boron, carbon, nitrogen, and oxygen and fluorine. For this second period, octet rule is perfectly suitable. So, octet rule is useful for writing the Lewis structure for the molecule with the second period of an element as a central atom. Okay, so that there are three exceptions of octet rule. So, there are three exceptions of octet rule. There are three exceptions. Three exceptions of octet rule. And the one is the first one here, incomplete octet. What is that? Incomplete octet. Incomplete octet. Incomplete octet is nothing but the molecule with electron deficient central metal atom. Molecule with electron deficient central atom. Electron deficient central atom. That is less than 8. Less than 8. Then the second one, a molecule containing all electron. Molecule contain odd electron. Odd electron. Molecule contain odd electron. And the third exception is superoctet. What is that? Superoctet. Superoctet. What is a superoctet? That means molecule with the expanded valence chains. Molecule with expanded valence chain. Molecule with expanded valence chain. So here there are three exceptions in writing the Lewis structure for octet rule. Here one is incomplete octet. What is an incomplete octet? It is less than 8 electrons around the central atom. And the molecule contains odd electrons. It is 1, 3, or 5, or 7 odd electron molecules is also stable. And superoctet. And molecule have more than 8 electrons. It is also stable by writing the Lewis structures. Okay, please see one by one. Clearly, the first one, molecule with the electron deficient central atom. So that here we are taking the molecule with the electron deficient central atom. So the first exception, molecule with electron deficient central atom. Electron deficient central atom. Central atom. Oh, listen. We are taking this one, the molecule with the electron deficient, that is not perfectly 8 electron of the atom in a molecule, and it may be less than 8. For example, we are taking, that is a molecule with less than 8 electron. We are taking the example, that is BF3 and BCl3 and BeCl2. Beryllium chloride. These are all exception of molecule with the octet rule. Suppose we are taking theory, that is let's consider boron trifluoride. So consider boron trifluoride. Consider, that is BF3. Now listen. While taking the BF3, first we want to find out the total number of valence electrons and the skeletal formula. What is the skeletal formula? So we are taking, that is boron is a central metal atom. Why? Boron is less electronegativity than the top fluorine. So the less electronegative atom should be in the center, except hydrogen and oxygen. Okay. Now we are taking, that is boron trifluoride. So it is F and that F and that F. It is the central metal atom boron, and here 3 fluorine. Now we are making, that is total number of valence electron. So listen, we are taking, that is total number of valence electron. Total number of valence electron. What is it? 1 boron. So boron, that is 1 into boron plus 1 into boron and plus 3 into fluorine. So what is that? 1 into 3 plus 3 into 7. So totally 24 electron. Correct? Now we are writing up the skeletal formula, that is BF3, and making a single bond first. So what is it? Here one single bond, and here one single bond, and here one single bond. So out of 24 electron, we are utilizing, that is a 6 electron by single bond. So that for single bond, that is 6 electron is utilized. Okay. Now remaining 18 electron. Remaining 18 electron we want to distribute with the highest electronegative atom as a orbit, as octet. So we make an octet with the highest electronegative atom. So there are 3 fluorine. Fluorine is highest electronegative atom. So these 18 electron is distributed towards the fluorine. So that here fluorine, that is 6 electron. And here 6 electron for fluorine, here 6 electron for the fluorine atom. Correct? So we are distributing remaining 18 electron towards the fluorine. Why? Because highest electronegative atom should be the octet. Now each fluorine is octet. Correct? Now we are taking that octet. So here, that is fluorine as octet structure. So that it is 8 electronic configuration. So that here it is 8 electronic configuration, and this fluorine also 8 electronic configuration. So that here it is 8 electronic configuration, 8 electronic configuration, and here this fluorine also it is 8 electronic configuration. 8 electronic configuration. So that here it is 8 electronic configuration with that bond pair and that lone pair. Okay. So these are 8 electronic configuration with that fluorine. So that here fluorine. Now we may take that for boron. We are taking a boron. Boron has only 6 electrons surrounded. That is 3 bond pair. Correct? So while doing the boron, the boron, we are taking this one. Here we are taking the boron. Boron has only 6 electrons. Correct? Boron has only 6 electrons. So we are taking boron has only 6 electrons, but fluorine getting that octet. So that here boron has only 6 electrons. Now we will take the formal charges of boron. So we are taking formal charge. Formal charge. Formal charge of boron. Formal charge of boron. So formal charge of boron, that is, what is that formal charge formula? That is valence electron become 3 for boron minus number of lone pair, it will be become 0 and plus number of bond pair by 2, so 6 by 2, so that here it is 0. So what is the formula? Here that is formal charge. Formal charge is nothing but number of valence electron minus number of lone pair plus number of bond pair by 2. Correct? So we will take the formal charge of boron. So boron has a 0 formal charge, so that it is a 0 formal charge. 0 formal charge. Now all the fluorine atom lies same, so that we are taking that is a formal charge. Formal charge of fluorine. Formal charge of fluorine. So what is that? Fluorine. The valence electron becomes 7 and the number of lone pair, that is 6 lone pair, that is 3 lone pair, that will become 6 electron and plus number of bond pair, that is 2 by 2, so that here also 0, so that in all fluorine it has 0 formal charge. It is also 0 and here also 0 formal charge, so that the molecule is most stable. So all the electron, it is, we are considered, it is a structure 1. It is structure 1. So the structure 1, even though bromine has only 6 electrons, bromine has only 6 electrons, but the formal charge of all atoms in the BF3 molecule is 0, so that it is most stable. So what is the conclusion here? In structure 1, so that here we are taking that is a note, and structure 1, all atoms as the formal charge, is equal to 0. Correct? So that the structure 1 is most stable structure. Most stable structure. Okay. Now, if you are writing that the same BF3 with different structure, suppose we want to move a lone pair towards a boron. So, yeah, one fluorine atom. The lone pair of fluorine atom is moved towards the boron, that we are getting the different structure. We are getting the different structure. Suppose we are taking that is the structure 2 for BF3. So that here it is structure 2 for BF3. So we are taking the structure 2, we are taking, listen. So that here that is a boron, and here fluorine, and here that is a fluorine, and here that is a fluorine. Okay, and first we are taking a single bond, and here we are taking there is a double bond this fluorine and making that octet. So here 8 electron and 2 double bond. So that 1 double bond with 6 electron, and here 1 double bond with the 6 electron. Now here we are making a double bond. Now we are taking that is a single bonded fluorine. and fluorine does not make the double bond first. So the structure is wrong, the first case. Okay, fluorine cannot making the double bond. Only carbon and nitrogen also making a double bond. So the structure is false itself. While taking the formal charge, suppose we are taking the formal charge of this fluorine. So formal charge is equal to, what is it? Here we are taking, that is a 7 minus, and lone pair, that is a 4 and plus 4 by 2. So that here it is a 6, so that it is plus 1. So this is the plus 1 formal charge. And here for this one we are taking, that is a formal charge is equal to, what is that? 7 minus, then that is a 6 lone pair, 6 electron, plus that is 2 by 2, so that it is equal to 0. So that here it is a 0. And here also the same, so that it is 0. For boron, we are taking, that is a boron. For boron, the formal charge. So formal charge is nothing but, that is 3 minus number of lone pair becomes 0 and plus number of bond pair, that is 8 by 2. Correct? That is 4 bonds, so that 8 electron. So that here it is minus 1. 4 by 2, so 4, so it is minus 1. So while comparing these two structures, which one is same? So listen, we are taking, that is these two structures, structure 1 and that structure 2. Structure 1 and that structure 2. So what is that? In structure 1, all are not getting their octets. Structure 1, only boron is electron deficient. Here, boron is electron deficient. Boron has only 6 electron, not a octet. Correct? Not octet. Okay. And here fluorine is 8 electron. So it is, that is the structure 1. 8 electron, then it is octet. Correct? In structure 2, what is that? Here boron and fluorine all are 8 electron and it is octet. And here in structure 1, formal charge. So here, that is structure 1, formal charge become 0. They are taking, that is formal charge is 0 for boron and that fluorine. And here we are taking, that is formal charge is, what is that? That is fluorine, maybe that is plus 1, that is doubly bonded fluorine, and single bonded fluorine, that it is 0, and for boron it is minus 1. So even though the second structure all are become octet, but the formal charge is not satisfied. So which one is most stable? Which one has all the formal charge become 0, then it is most stable. So that we conclude which structure is possible for BF3. So this structure is possible and it is not the correct structure for BF3. Okay, students, are you understand that? So here BF3, that is, even though it is deficient boron is there, but the molecule becomes most stable. So the correct structure is the structure 1, not the structure 2. Okay, now we may take the next one. So we are taking the next one. It is odd electron molecule. So what is that? Here the second one, it is odd electron molecule. So molecule with the odd electron. Molecule with the odd electron. With odd electron. molecule with odd electron. Listen. Here we are taking some examples of this, that is molecule with odd electron. Now we are taking the examples. The students, any doubt? The students, any doubt? With the molecule of
No, sir.
No, sir.
Are you hearing my words?
Yes, sir. Audible, sir.
Yes, sir.
Incomplete object. Any doubt?
No, sir.
Students, are you hearing me or not?
Yes.
Okay. Then we may continue this session. Here, the molecule with the odd electron. Now, we are taking the molecule and central atom with the odd electron is stable. So, molecule with the odd electron, molecule with odd electron as central atoms is also stable. For example, we are taking example, that is nitric oxide and N2, nitrogen dioxide. I take NO2 better. Nitric oxide and nitrogen dioxide. Okay, listen, we are taking here, that is first nitric oxide, NO, and the total valence electron. Total valence electron. So what is the total valence electron? And nitrogen 7 and oxygen 6. So that 7 and here oxygen it is 6. Sorry, nitrogen it is 5. 5 and that 6. That is totally 11 electrons. 11 electrons. Now we may make that the structure, that is Lewis structure for N. And the first one here, that is nitrogen, and here oxygen, that is making a single bond. Okay, and here we are taking, that is nitric oxide, and we are taking, that is 6 electron here to do that octet, and remaining, so what is that? Here we are utilizing totally 8 electron around the oxygen, remaining that is 3 electrons, so that here 3. Okay, now to getting an octet, this structure is converted into another one. So what is it? This bond is moved here. So what is it? We are taking, that is nitrogen, and here there is a double bond and oxygen, and here there are another 4 electron, and here it is 1 electron. Correct? Now nitrogen is getting octet. Correct? We are saying, listen, here the nitrogen is getting octet. So nitrogen is getting octet. Nitrogen is getting octet. Okay, 8 electron in nitrogen. And in the case of oxygen, oxygen getting octet. In the case of nitrogen, it has only 7 electron. Correct? There's only 7 electron. So here nitrogen has 7 electron. Nitrogen has only 7 electron, and it is not octet. Not octet. And here oxygen has 8 electron, then it is octet. Correct? So here oxygen has 8 electron and nitrogen has 7 electron. Now we may take a formal charge. So we have conclude the formal charge. So here the formal charge. Formal charge of nitrogen here, what is that? Here nitrogen, that is 5 minus number of lone pair, that is 3, plus number of bond pair, 2 bond pair, so that is 4 by 2. Then it is 3 plus 2, so that 5, it will become 0. And the formal charge of oxygen, and here, what is that? Here, that is 6 is the valence electron, and that is lone pair, that is 4, and the bond pair plus, that is 4 by 2, so that here 0. So both have 0 formal charge. So the correct structure is NO, even though it contains odd electron. Nitrogen has odd electron. Now we may take the second example, that is nitrogen dioxide. Nitrogen dioxide. So we are taking, that is nitrogen dioxide. And the structure of this nitrogen dioxide, here we are taking, that is oxygen and double bond nitrogen, and here that is oxygen. Okay, and the lone pairs, here that is 2 electron, and here 4 electron, and here it is 6 electron. And here we are taking the formal charge. Formal charge of doubly bonded oxygen, that is 0, and for nitrogen it is +1, and here it is -1. It is a -1, and it is the correct structure. And here we are taking this nitrogen which contains 1 more electron. So in nitrogen dioxide, total number of valence electron, nitrogen 5. So valence electron. So here 5 plus 12. Correct. 2 oxygen, so that it is 12, so that it has 17 electron. Now, how many bond? That is 3 bond pair, so that 6 electron, and remaining, that is 11 electron for single bond oxygen, that is 6, and double bond oxygen, that is 4, and remaining 1 oxygen, that is 1. So totally 11 electron. So 11 lone pair and 3 bond pair, totally 70 electron. While taking that, the formal charge, it is 0 plus 1, and that -1. So it is the correct structure, even if nitrogen getting odd electron. So nitrogen has how many electron here? That is 2, 4, 6, and 7 electron. So we are saying nitrogen. Listen, here nitrogen has only 7 electron, and that oxygen has 8 electron, so that it is octet and it is not octet. Not octet, but the molecule is a state. The molecule is a state. Okay, so this is odd electron molecule and the exception of octet group. And the next one we are taking, that is a super octet. What is that? Super octet. Super octet. Super octet are molecule with the expanded valence set. Molecule with expanded valence cell. Expanded valence cell. So super octet are molecule with the expanded valence cell. What is that? Here the atom has more than 8 electron is surrounded. So atom in a molecule, atom in a molecule is surrounded by more than 8 electrons. More than 8 electrons. Now we are taking examples, that is PCl5. PCl5 and that is SF6. PCl5 and that SF6. Okay, now we are taking the structure of PCl5. So listen, we are taking that is PCl5. Okay. Now here it is phosphorus and it is surrounded by that is chlorine. So here it is chlorine and here it is chlorine and here it is chlorine. Chlorine and here it is chlorine and here it is chlorine. Now it is surrounded by each chlorine is surrounded by that is a 6 valence electron, so that it has 6 valence electron. It is the structure of PCl5. These are the lone pair of electrons surrounded by chlorine. Okay. Now, that is in this case, what is that? Phosphorus. We are taking first phosphorus and the chlorine. Each chlorine has, listen, we are taking each chlorine is surrounded by 8 electrons. That is 6 lone pair electrons and 1 bond pair. Now, we are taking that is a phosphorus. Phosphorus is surrounded by 10 electrons, correct? So phosphorus is surrounded by 10 electrons. So we are taking phosphorus. It is surrounded by 10 electrons, so that it is a superoctet. That is, phosphorus has 10 electron, so that it is a superoctet. Superoctet. Okay. Now we are taking that is S sub 6. The molecule that is S sub 6. So we are taking the molecule. Listen, it is SF6. Okay. In SF6, we are taking SF6 molecule. That is, here it is a sulfur, and we are taking make a bond. Here one bond, here one bond, and here one bond, here one, like this. Then it is filled by fluorine. So that fluorine. Now, we are taking there is a sulfur. Sulfur is surrounded by how many electrons? Sulfur is surrounded by how many electrons? There are 12 electrons, correct? So sulfur is surrounded by 12 electrons. Sulfur is surrounded by 12 electrons. So that here this sulfur contains 12 electrons. Sulfur contains 12 electrons, so that it is a superoctet. Superoctet. And all fluorine is surrounded by that is 8 electrons, so that here there are 8 electrons, so that it is octet. Correct? So a molecule with more than 8 electrons is also stable, and it will accommodate the excess electron by this p orbital, so that the central atom accommodates the additional electron. Central atom accommodate additional electron by its expanded octet. Expanded valence shell. Expanded valence shell. So this is superoctet. This is a superoctet. Okay, so this is the exception of octet rule. Exception of octet rule. So listen, students, we are taking the exception of octet rule. Now we are taking that is ionic bond and the electrovalent bond. So listen, we are taking that is ionic bond and the electrovalent bond. Listen, students. So the next topic, it is ionic bond. Ionic bond. Okay, listen. So what is an ionic bond? So ionic bond is nothing but it is a strong electrostatic forces of attraction between the ion. Ionic bond is nothing but defined as the strong electrostatic attraction between oppositely charged ions which are formed by transfer of electron. Is known as ionic bond. So here, a strong electrostatic forces of attraction between oppositely charged ion. This oppositely charged ion is formed by complete transfer of electron, which is known as ionic bond. It is a simple definition of ionic bond. Okay, now we are taking an example, that is KCl, potassium chloride. Potassium chloride, here we are taking, that is potassium. Potassium, it has 19 atomic number, and its electronic configuration, it is argon, that is 18, and that it is 4s1. Okay, and we are taking that is chlorine, and it has 17 electron atomic number, so that its electronic configuration neon, and it is 3s2 3p3. 3s2 3p3. These are the electronic configuration of potassium and the chlorine. Okay, listen here. In the case of potassium, it will be loses one electron, then it will become another electronic configuration. So that here we are saying that is the potassium, and it will be loses one electron, then it will become the K plus electron, and its electronic configuration becomes that is argon. So that here it is argon electronic configuration, that is 18 electronic configuration, and it is nothing but removal of electron. Removal of electron is nothing but ionization energy. So its ionization energy enthalpy, that is delta H value is, that is 418, that is 418.81 kilojoule per mole. Correct? So while potassium lose one electron, and become argon electronic configuration, which is more stable. And in the case second, what is that? When we are taking that is a chlorine, and chlorine will accept one electron. Chlorine will accept one electron and become that is a Cl minus. Now it is getting the argon electronic configuration, so that it is argon electronic configuration, so that we are getting cation and the anion. So in third case, what will happen? These two ions, what is that? The cation. What is that? Here we are taking in the first case. This is ionization energy. What is that? It is ionization energy. And the second case, it is electron affinity, accepting electron. So the amount of energy released and moreover, gaseous neutral atom accept an electron, become an anion. So that it is electron affinity. So this enthalpy is minus 348.56. It is minus 348.56 kilojoule per mole. Okay. Now, in third case, what will happen? This cation and the anion. So, what is the cation here? That is K plus cation. It is argon electronic configuration is attracted by the Cl minus, that is the anion, and form the KCl, that is ionic crystal. Ionic crystal. Okay. But here the ionic crystal formation, that is the delta H value for 1 mole of K plus is attracted by 1 mole of Cl minus, and here the delta H value is crystal formation is delta H of crystallization is, that is 718 kilojoule per mole. 718 kilojoule per mole. Okay, but while doing this one, and we are getting only 70.25. Correct? Here we are getting only 70.25, but this formation of K plus and Cl minus, K plus and the Cl minus is, that is 780 kilojoules per mole. So that the strongest attraction between K plus and the Cl minus is there. So that the ionic crystal is more stable. So we are taking the ionic bond. And what is the ionic bond? Ionic bond is nothing but the strong electrostatic forces of attraction between oppositely charged ion. Here the K plus is attracted, Cl minus ion, and form the ionic crystal, and which are formed by transfer of electron. Now, by transfer of electron, each atom getting the octet electronic configuration. So, octet electronic configuration is most stable. To attain this octet electronic configuration, and the atoms are shared is valence electron, or loss is valence electron, or gain is valence electron, and to loss or gain or share, it will become the stable electronic configuration, that is octet electronic configuration. So potassium lose 1 electron, becomes stable argon electronic configuration, and chlorine gain 1 electron and become that Cl minus, and it is argon electronic configuration. So that there is a ionic crystal that will be formed with K plus is attracted by Cl minus and form KCl crystal. So this is ionic bond. Now we are taking, there is 2 topic here, exception of octet rule and the ionic bond formation. And there are 3 exceptions. One is incomplete octet and odd electron molecule and that super octet. Incomplete octet generally boron family as incomplete octet. And here we are taking the 2 structure of BF3, and by getting the formal charge we may select one. The structure 1 is most stable, and we are taking the second one, odd electron molecule, that is NO, and NO2 is odd electron molecule. In this nitrogen has only 7 electron, but it is a stable. And the third one, it is a superoctet. In the case P sulfide and SF6, phosphorus has 10 electron and sulfur has 12 electron. It is more than 8 electronic configuration, but here it is most stable. While doing the formal charge of phosphorus and sulfur, it will become 0. So it is most stable electronic configuration. After that, we are taking ionic bond. Ionic bond is nothing but there is a strong electrostatic forces of attraction between oppositely charged ion, and this charged ion is formed by transfer of electron. And by transfer of electron, each atom getting the octet, so that the anion and the cation is attracted and form the ionic crystal. Okay, any doubts, students?
No doubt.
Any doubt?
No, sir.
No doubt.
No, sir.
No, sir.
Any doubt, students? In exception of octet rule and ionic bond formation.
No, sir.
No, sir.
Sir.
No, sir.
No one is replying. Shall I ask a question?
Yes, sir.
Yes, sir.
Ratin
Yes, sir.
in 11th C. Example of superoctet. Ratin, say the answer. Example of superoctet. Joshida. I think Ratin is leaving. Okay. Thank you, students.